Welcome back to the deep dive.
For the last few years, it feels like our entire discussion about, well, the future of general purpose AI has really revolved around text large language models.
Yeah, absolutely. LLMs became the bedrock, right? The sort of foundation model that everyone assumed could eventually handle pretty much any symbolic task you threw at it.
But now it feels like the focus is really shifting. Suddenly, that same blueprint, the idea of one massive generative model mastering everything, well, it's moving decisively into the realm of vision.
It really is. And that's what we're diving into today. We're looking at some fascinating new research from Google DeepMind, where they've analyzed their latest generative video model, VO3.
And the findings, I mean, they're comparing VO3 to its predecessor, VO2, which only came out a few months before it. And the researchers themselves, they're actually calling this the GPT-3 moment for vision.
Which is a huge claim. That's not just hype, right? It's suggesting a really fundamental shift architecturally and, well, philosophically in how we even approach machine vision.
Exactly. So our mission today really is to dig into that claim. Is it justified? Can these big generative video models actually achieve what we'd call general purpose vision understanding?
hmm And specifically, can they solve problems they were never explicitly trained for? That's the key, isn't it?
Mhm.
We're looking for solid evidence of zero-shot learning, across the whole visual stack, everything from just recognizing shapes.
All the way up to simulating complex physics, maybe even doing some abstract reasoning.
Precisely. Because if you look at machine vision today, I mean, it really does resemble where natural language processing was, what, maybe 5 or 6 years ago?
Totally. We've got these amazing task-specific systems. You need top-notch segmentation. Okay, you grab segment anything.
Right. Or real-time object detection, use a YOLO variant, or something similar. These models are incredible, but they're masters of just one narrow domain.
They're siloed. They're all like bespoke tools for specific jobs.
Exactly. There's no single unified system that just does it all. So the analogy holds up perfectly. We're hunting for the visual equivalent of that generalist language model.
The one you can just prompt, you just tell it what you want, translate this, summarize that, write some code, answer a complex question.
All without messing with the underlying architecture, without needing specialized training data for every single new thing you ask it to do.
And VO3, based on this research, seems like maybe the most compelling candidate we've seen so far to actually usher in that generalist era for vision.
Yeah, let's maybe just establish that context first,
Yeah, go.
because understanding just how radically LLMs transform language is, I think, really key to appreciating what might be happening now in vision.
Good point. So rewind to the late 2010s. The NLP world was all about those specific, often hand-tuned models, right?
Absolutely. If
Yeah.
you needed, say, machine translation, you trained a model just for translation, probably some complex sequence-to-sequence thing, custom architecture.
And then if you decided, okay, now we need a question answering system, you essentially started over. Different architecture, maybe a custom CNN or RNN layer.
And you'd stick a custom inference head on the end, something only capable of spitting out answers in the right format for that specific task, nothing else.
It was incredibly resource intensive, fragmented.
Totally. And the revolution, the big shift, came when we basically threw out all those different architectures and specialized heads. We settled on that simple, unified, decoder-only transformer structure.
And crucially, the training objective itself got stripped right back to basics. Just predict the next word, text continuation, train it on basically the entire web.
And that was the magic, wasn't it? The LLM era showed us that general-purpose intelligence wasn't something you had to explicitly program in task by task. It just emerged. It was a scaling law.
Right. Make the models big enough, feed them enough data, and suddenly this simple generative task predicting the next token starts giving rise to these incredibly complex abilities. Mathematical reasoning, logical deduction.
Writing complex code. You didn't fine-tune GPT-3 specifically to write poetry. That ability just sort of popped out as a consequence of the scale needed to get really good at basic language prediction.
Okay, so if we take that entire paradigm, that whole playbook, and apply it to vision, the big question is, can the exact same principles work? Can we use those same simple primitives, huge scale, a generative objective, web scale data, and get a similar emergence of zero-shot capabilities, but visually?
Well, this DeepMind research around VO3 makes a pretty strong case that the answer is yes. The generative video model, it's trained on a fundamentally simple visual primitive,
Which is?
generating a continuous sequence of high-fidelity frames based on a text prompt or maybe an initial image. It's essentially video continuation, like text continuation, but with pixels.
Ah, okay. And just like with the LLMs, scaling that simple primitive is what leads to the general purpose stuff.
That seems to be the idea, the ability to do things like segment objects or detect edges or edit images or even simulate physics. These apparently weren't programmed in as separate skills.
They just emerged.
Yeah.
Zero shot.
Exactly. Simply because for the model to get really good at generating plausible, coherent video, it had to implicitly learn a highly accurate, generalized model of the world.
Wow. Okay, so that really drives home takeaway one then. The era where you needed a different specialized vision model for every single little task.
Yeah.
That might genuinely be ending.
It looks that way. Prompting, just telling the model what you want visually, instead of doing task-specific training or complex architectural changes that seems demonstrably on the horizon for machine vision.
And it's these huge generative video models that are making it possible. You give it an image, a complex visual instruction, not code, not a fine-tuning data set, and it just does it.
That's the promise. And look, this isn't just theoretical speculation. It's quantifiable, and it seems to be happening incredibly fast.
Right. You mentioned the comparison. For you listening, the DeepMind research, it rigorously analyzed, what was it, over 18,000 generated videos.
18,384, yeah. Across 62 qualitative tasks and 7 quantitative ones using VO3, which came out in July 2025.
But the key is comparing it to VO2.
Exactly. VO2 was released just 3 months earlier, April 2025. And in that roughly half-year gap between versions, the researchers saw what they called a substantial and consistent performance improvement.
Substantial and consistent in just a few months.
Yeah. That kind of rapid jump in capability in such a short window, it really mirrors that exponential growth curve we saw when LLMs were scaling up rapidly.
It suggests these vision models are still very much accelerating up that curve, maybe doubling in competence every few months. Who knows?
It certainly points in that direction.
Okay, so let's unpack these emergent abilities then. The research actually gives us a really helpful way to think about them. They organized VO3's zero-shot skills into 4 categories, kind of like a hierarchy: perception, modeling, manipulation, and reasoning.
And they build on each other, which is
Right.
quite intuitive. It helps us maybe understand the model's, I guess, internal cognitive structure, if you can call it that.
So perception is the foundation, just the basic ability to see and analyze what's in the visual input.
Right. And historically, like we said, this needed those specialized models. If you wanted to, say, find the outline of an object, you needed a dedicated edge detection model.
But VO3 seems to be doing a whole bunch of these classic, highly tuned computer vision tasks just out of the box without specific training for them.
That's what the research indicates. It's showing this kind of intrinsic understanding of boundaries, structure, features.
What kind of specific tasks are we talking about?
Well, things like generating pretty clean edge detection maps or finding key points, like corners or important features on an object. And even instance segmentation, identifying and outlining specific individual objects within a crowded scene.
Okay, so that's foundational visual competence, but achieved zero shot.
Exactly. But it goes further than just analysis. It also seems quite good at restoration and enhancement tasks.
Like making images better.
Yeah. The research showed it performing zero-shot super resolution, taking a low-res image, and significantly boosting its detail. It also demonstrated blind deblurring, sharpening blurry images without knowing the blur type, and pretty robust denoising.
Denoising, like removing graininess.
Right. And interestingly, not just general noise, but it handled very specific, technically distinct types of noise, things like Gaussian noise, salt and pepper noise, speckle, even shot noise.
Wow, that suggests a really fine-grained understanding of how images can get degraded.
It seems so. And it also did low-light enhancement, apparently leveraging principles similar to those in specialized datasets like LOLv2 to brighten up dark images and bring back detail.
Okay, this is where it gets really interesting, I think, because the tasks start to move beyond just standard computer vision and into territory that challenges even human perception, like ambiguity.
You mean like the classic Dalmatian illusion?
Exactly. That picture that's just a mess of black and white spots until suddenly your brain clicks and you see the dog.
Yeah, a standard segmentation model would likely just see spots. It struggles because the dog's outline isn't explicit. It's implied by the pattern.
But VO3, it manages to see the dog.
Apparently so. The researchers suggest it's because the model needs to maintain that internal visual coherence for generating video, so it learns to group features into meaningful wholes.
That makes sense. What else?
Well, similar things with visual cue conflict images. Like, there's an image designed so the texture suggests one thing, but the shape suggests another. Maybe the cat shape made of, I don't know, brick texture. VO3 could still identify the cat shape, prioritizing shape over conflicting texture.
And even more abstract stuff, right? Like Rorschach blots.
Yeah. It could generate plausible, concrete interpretations of those ambiguous ink blots, turning these abstract patterns into recognizable objects, which is basically a form of visual projection, assigning meaning to vague input.
Wild. And there was one more perception test mentioned. Conjunctive search? What's that?
That relates to something called the binding problem in cognitive science. It's about how our brain links different features together, like color and shape and location.
Okay.
So they tested VO3 by showing it a scene with lots of different colored balls, and they prompted it to make only the blue ball glow.
And could it do it?
Yes. It successfully bound the property glowing to the specific feature blue color and applied it correctly, ignoring the other balls. It shows it can manage multiple visual attributes precisely and simultaneously.
Okay, so this brings us to takeaway 2 then. This feels pretty critical, especially for anyone working in computer vision today.
I think so. The argument is, once the cost comes down, and we should definitely talk about the economics later, but once it's affordable.
These emergent zero-shot perceptual abilities for models like VO3 could potentially just cannibalize most of those bespoke, specialized computer vision models we use today.
Right. Why would you maintain a whole stack of different tools? One for segmentation, one for edge detection, one for super resolution, when a single large generative model might be able to handle all of them just through simple text prompts.
That's a powerful argument.
So if perception is about seeing the world, modeling is the next layer up. It's about the model starting to grasp the underlying rules, the governing principles, basically intuitive physics.
This internal world model, it must be crucial for generating video that actually looks believable, right?
Absolutely essential.
Yeah.
If the model doesn't understand basic physics, the videos it generates are going to look wrong very quickly.
And the examples they gave here, some of them really seem to probe a deep understanding of, like, material science and mechanics.
Yeah, they showed VO3 simulating pretty complex physical properties, things like rigid body dynamics, how solid objects move and interact, but also soft body dynamics.
Soft bodies, like cloth.
Exactly. One example that stood out was simulating draping a thin silk scarf over a vase.
Okay, that sounds tricky.
It's really tricky. Think about what's involved. You need to simulate the fluid-like dynamics of a very light material, the forces of gravity, air resistance acting on this soft, deformable thing,
How it folds over itself, self-occlusion.
and how it continuously interacts with the rigid surface of the vase underneath. I mean, dedicated physics simulation engines can struggle with that kind of complexity.
And VO3 managed this zero shot, just from a prompt.
Apparently so, which is a pretty massive indicator of a surprisingly powerful internal physics model.
It wasn't just small-scale stuff either, right? Didn't it handle bigger physics concepts?
They showed it modeling objects falling on Earth versus falling on the moon.
Whoa! So it has to generate different gravitational pulls
Okay.
and air resistance effects.
Implicitly, yes, to get the motion right in both scenarios. And it also correctly simulated buoyancy. They showed it making a bottle cap float while a rock sank when both were released in water.
Which implies it understands things like density and displacement relative to the water.
It certainly suggests that. And the model seems to move beyond just basic dynamics into more sophisticated stuff, like object interactions and even understanding categories.
You mean like the visual Jenga task?
Yeah. It was prompted to remove blocks from a stacked Jenga tower. And it apparently did it in a sequence that was physically plausible. It didn't just pull out a bottom block and have the whole thing collapse instantly. It seemed to understand the stability constraints.
That's pretty cool. And what about object packing?
Another great example. It showed an understanding of which objects like soft, squishy toys versus a hard rectangular laptop would actually fit inside something like a backpack or a bucket.
So it's kind of implicitly categorizing objects based on how compressible they are, their shape constraints.
Seems like it. And the modeling capabilities even extended into optics.
Optics, like light.
Yeah. It correctly generated optical phenomena, like showing light refracting as it passes through a glass sphere versus reflecting off a highly polished mirror sphere.
Is there a visual difference it captured?
Critically, yes. The image seen through the refracting glass sphere was inverted, flipped upside down, which is optically correct. But the image reflected on the mirror surface was not inverted.
Huh. Okay, that shows a surprisingly sophisticated grasp of, like, basic geometric optics, implicitly anyway.
And it even got abstract relationships, like color theory. It could simulate additive color mixing, how lights combine. You know, red and green light make yellow.
Versus subtractive color mixing, which is how paints work, where red and green paint make a muddy brown.
Right. Those systems follow different rules, but VO3 could apparently generate videos following either set of rules correctly, depending on what the prompt asked for, lights or paints.
That's quite specific. And one last thing in modeling. Memory. World states.
Yeah, this is vital for video. You need coherence from one frame to the next, obviously, but also across bigger changes.
Like camera moves.
Exactly. They demonstrated VO3 zooming right in for a close-up on a person, and then zooming back out to the original wide shot. And importantly, the person was still in the same place, looking consistent.
So it maintained the object's integrity and location across that big camera change.
Which indicates it has some kind of robust internal memory, a persistent representation of the scene that isn't just tied to the current camera angle or the pixels in the last frame. It understands the underlying 3D scene.
Okay, so if perception is seeing and modeling is understanding the rules, manipulation is the next step. Actually altering that perceived and modeled visual world based on instruction.
Right. This is where you get into more advanced editing capabilities, but also imagination, creating things that weren't there before.
And VO3 seems to treat image editing just as another video generation task.
Pretty much, yeah. Performs a lot of standard, complex image editing tasks, zero shot. Things like robust background removal, colorizing black and white images, in-painting.
In-painting. Filling in missing bits.
Yeah, like a part of an image is corrupted or masked out. It can fill it in plausibly.
Yeah.
And also outpainting, extending the scene beyond the original picture's boundaries, imagining what might be just outside the frame.
We also saw examples of complex style transfer. I think the paper mentioned turning a normal scene into the style of Hunderwasser.
That's right, that very intricate, organic, almost psychedelic style. Applying that consistently to a whole scene is non-trivial.
And on a more practical level, something maybe more relatable for listeners, turning a basic selfie into a professional headshot.
Just by prompting it, apparently. Telling it to make the necessary visual edits, maybe change the background, adjust the lighting, even subtly tweak the pose or expression to get something that looks like a proper, polished LinkedIn photo.
That's potentially very useful, and this ties into its 3D awareness.
Definitely. That ability to understand the underlying 3D structure allows for more advanced imagination. It can generate novel views of objects or characters if you give it just a single starting image.
And 3D-aware reposing, what was the example there?
They showed it generating a sequence where a knight character smoothly changes pose, like starting standing up, then dropping realistically down onto one knee, all while maintaining physical presence, lighting consistency.
So it understands how the body parts connect and move in 3D space.
It seemed to have a good handle on that. And maybe the most, well, magical-sounding example was transfiguration.
Right. Turning one object into a completely different one.
Yeah, like a teacup smoothly morphing into a mouse, almost like a visual spell effect. Now, they were clear the success rate on this extremely hard task was low, like 17%.
Okay, so it didn't always work.
No, far from it. But the fact that a video generator could achieve a reasonably coherent visual transition between two totally different objects at all, even sometimes, that really speaks volumes about its underlying generative power and maybe its understanding of object properties.
And finally, under manipulation, there was simulated dexterity and affordance.
Yeah, this is about imagining how things, like maybe robot hands, would interact with objects.
So simulating complex actions.
Things like robot arms unscrewing the lid of a jar or throwing and catching a ball. These are multi-step actions requiring coordination.
And affordance. That's about understanding how objects are used.
Exactly. The classic example is a hammer. If you prompt the model to show a robot hand picking up a hammer, does it grab it by the heavy metal head or by the handle?
And VO3.
It correctly grasped it by the handle, which indicates it has some implicit understanding of object affordances, how an object's shape and function dictate how you interact with it.
Okay, this feels like the top of the pyramid. Reasoning, where the model integrates everything, perception, modeling, manipulation to solve problems that need, like, step-by-step logic.
Exactly. And this is where the analogy to large language models becomes really direct and, I think, quite profound.
You mean the chain of thought idea?
Precisely.
Yeah.
In LLMs, we discovered chain of thought, or COCA, this technique where the model breaks down a complex problem into intermediate symbolic steps, writing them out before giving the final answer. It dramatically improved reasoning performance.
And the video model has something similar.
Well, think about the inherent nature of video generation. It generates one frame, then the next frame condition of the first, and the next condition on the previous ones. It's sequential by definition.
Okay.
This frame-by-frame generation process provides a natural, visual, temporal parallel to the symbolic, sequential process of chain of thought. The researchers are calling it the chain of frames, or COF.
Chain of frames. I like it. So this COF mechanism lets the video model reason across time and space visually. Each frame is like a step in a logical process.
That's the core idea. And it seems to unlock these early but still impressive forms of emergent reasoning capabilities.
What kind of reasoning tasks could it handle?
We saw examples in things like pathfinding and planning. It could solve fairly complex mazes, like generating a video of a mouse navigating its way to find some cheese.
Okay, that requires some foresight, remembering where it's been.
And also robot navigation tasks, like guiding a simulated autonomous vehicle towards a specific target, like a blue-colored area in a complex environment.
What about more abstract logic?
It tackled logical sequence completion tasks, inspired by things like Raven's progressive matrices, those psychological tests with pattern sequences.
Right, like figuring out the next shape in a series.
Yeah, completing patterns involving, say, arrows changing direction, or circles shrinking, or squares growing according to a rule. And it even attempted puzzles.
Puzzles, like Sudoku.
Simple ones, yeah, like 4x4 Sudokus. And also things like water puzzles, where you have interconnected containers and you need to figure out the order they fill up in. VO3 could simulate the correct liquid transfer dynamics.
That requires understanding both logic and physics.
It does. And maybe one of the most complex examples was tool use, which is often seen as a hallmark of higher intelligence.
What was the task there?
Generating a sequence showing how to retrieve a walnut that's sunk to the bottom of an aquarium using some kind of tool.
Okay, that's definitely multi-step. You need to understand the goal, the limitations, can't just reach in. Identify a suitable tool, figure out how to use it.
Exactly. It integrates perception, planning, and manipulation. Now, the researchers are very careful here. They state clearly that these reasoning abilities are not always perfect.
Right. It's not like it's acing every logic puzzle.
No, definitely not. But the key insight, again, is that these capabilities are emerging. Zero shot. The fact that a model trained simply to generate video frames is starting to exhibit this kind of structured visual reasoning and planning.
That really points towards the next major frontier for these generalist foundation models. It's not just about pretty pictures anymore.
Not at all. It's about visual intelligence.
Okay, so we've talked a lot about these qualitative sparks of intelligence, these really cool examples. But the research didn't just rely on anecdotes. They backed it up with quantitative numbers, right?
They did. They included 7 quantitative assessments, specifically chosen to test capabilities across perception, manipulation, and reasoning. And crucially, they compared VO3 not just to VO2, but also to some leading specialized models in certain tasks.
Before we get into the results, let's quickly clarify the metrics they used, because there was a distinction between best frame and last frame.
Yeah, that's important. The best frame score represents the model's peak performance on a task, like somewhere within the generated video sequence, it achieved the correct result. This shows the model's potential ceiling.
But it's not very practical because as a user, you don't necessarily know which frame is the best one.
Exactly. The last frame score is more practical. What's the result at the very end of the generated video? But this often underestimated VO3's ability.
Why is that?
Because the model seems to have this strong bias, this prior, to just keep animating things. So sometimes it would solve the task correctly, say halfway through the video, but then it would keep adding extra unnecessary animation afterwards, potentially messing up the final frame score, even though it has solved it earlier.
Okay. That makes sense. And they also use this Passat K metric, specifically by Passat $10.
Right. Passat K means they run the same prompt, $10, generate different video attempts, and then score the best result out of those dollar attempts. They focused on Passat $10.
And why is that significant?
Because it reflects a practical way these models might be used. If inference is cheap enough, you can just run the prompt multiple times and pick the best outcome. And they found that performance consistently improved, often substantially, when going from $1 just one try to $10 10 tries. It shows that multiple attempts can overcome some of the model's inconsistency.
Got it. Okay, so let's look at the perception metrics first. They started with edge detection using a standard benchmark dataset called BIPEDV2.
BIPDB2 is commonly used to test how well models can find object boundaries. VO3 achieved a score of 0.77 pass at 10 on this.
How does that compare? Is 0.77 good?
It's respectable, especially for zero shot. It's definitely below the absolute state-of-the-art for models specifically trained only on edge detection. But here's where it got really interesting.
What happened?
Qualitatively, when they looked at the actual edge maps VO3 produced, many of them were actually more detailed and accurate than the supposed ground truth labels in the BIPDV2 dataset itself.
Like, how is that possible?
Well, VO3 was picking up fine details like outlining individual leaves on distant foliage or tracing the precise tread pattern on a car tire. These are details that the human annotators who created the dataset often skipped over, probably because it's incredibly tedious work.
So it's like the generalist model was actually too good for the specialized benchmark. It revealed limitations in the evaluation data itself.
Kind of, yeah. It suggests the model's perceptual ability might actually exceed what the current benchmark can even measure properly in some cases.
That's fascinating. Okay, what about segmentation? Identifying and outlining objects.
For that, they used a subset of another common dataset, LVIS, Large Vocabulary Instance Segmentation. VO3 reached a mean intersection over union, or MIOU, score of 0.74. Again, that's using the best frame pass at 10 metric.
And how does 0.74 stack up?
That's directly comparable to a leading specialized image editing model called Nano Banana, which scored 0.73 on the same task.
So VO3, a general video generator, is matching a dedicated image editing model, zero shot on segmentation.
Pretty much neck and neck, yeah, which is impressive. But there was another interesting wrinkle here related to prompting.
Oh, yeah.
Performance wasn't consistent. It depended significantly on the prompt details. Specifically, VO3 did much better at segmenting the object when the prompt asked for it to be placed against a green background, getting that 0.74 score, compared to a white background where the score dropped to 0.66.
Green background versus white, why would that make such a big difference?
The researchers speculate it's a learned prior from the training data. Think about how much video footage uses green screens for compositing, for isolating subjects.
So the model has probably learned a strong association. Green background likely means the task is about isolating the foreground subject.
Exactly. It's essentially exploiting a shortcut, learned from practical video production techniques that were heavily represented in its training data. It gives us our first strong hint about how crucial visual prompt engineering is going to be.
Makes sense. Okay, let's move to the manipulation metrics. Object extraction and counting.
Right. This task was about identifying a specific number of animals in a scene, say 3 sheep, and then generating a video where those 3 sheep are extracted and lined up.
How did VO3 do?
It showed a really radical improvement here. It achieved up to 93% pass at 10 accuracy on correctly extracting and lining up the specified number.
93%. That sounds high. How did VO2 do on this?
That's the kicker. VO2, the predecessor from just months earlier, performed basically around chance level on this task. It really struggled with object integrity counting.
Wow, so that jump from chance to 93% accuracy in just one version iteration, that shows incredibly rapid progress in the model's core understanding of objects, categories, and how to manipulate them robustly.
It really does. It suggests those foundational modeling capabilities solidified very quickly between versions.
What about standard image editing performance? They used a benchmark called EmuEdit.
Yeah. Here, the results were more nuanced, showing a clear trade-off. VO3 was generally very good at fidelity, meaning it made the correct type of edit requested by the prompt.
So if you asked it to change the color of something, it changed the color correctly.
Right. And it was also good at preserving existing details and textures in the parts of the image that weren't supposed to change.
Okay, but what was the trade-off? Where did it struggle?
Precision control. Because it's fundamentally a video model designed to create motion, it often had trouble keeping the theme perfectly static when a static image edit was requested.
So it would introduce unwanted changes.
Yeah, things like subtle camera movements or slight unnecessary animations happening in the background, or even to the object being edited, when the goal was just a single static edited image. That lack of precise control was its main weakness there.
Got it. Okay, finally, the reasoning metrics. Let's start with maze solving.
This is where that chain of frames concept really seemed to shine. VO3 achieved a 78% success rate, pass at 10, on solving 5x5 grid mazes.
And VO2?
Only managed 14%. It often made illegal moves, like going through walls, very early in the generated video sequence.
So another massive jump between versions, suggesting the reasoning capability improved dramatically.
Absolutely. And the comparison to Nano Banana, the image model, was also telling here.
How so?
Nano Banana completely failed on mazes that weren't perfect rectangular grids, like irregular mazes. It just couldn't handle them. Even powerful LLMs struggle if you just show them the maze as an image. They do better if you represent it as text, like ASCII characters.
But VO3, solving it visually, frame by frame,
could leverage its internal spatial model and the sequential COF process to navigate successfully, even in complex, irregular layouts. It really highlights the advantage of a visual, step-by-step reasoning approach for this kind of spatial task.
What about visual symmetry? Completing patterns.
Here again, VO3 significantly outperformed both VO2 and Nano Banana. When prompted correctly, it showed a good understanding of spatial relationships and could complete patterns symmetrically.
Okay, sounds positive. But then we get to visual analogies using the Kiva benchmark. And here things got weird.
Yeah, this was probably the most puzzling result. VO3 was excellent, performed really well on analogies that involve transformations like changing color or resizing objects.
So A is to B as C is to kind of thing, involving color or size changes.
Exactly. It nailed those. But then, for analogies that required geometric transformations like reflecting an object across an axis or rotating it by a specific amount,
It failed.
it performed below chance,
Yeah.
which is worse than just guessing randomly.
Wait, that seems like a huge contradiction. How can it be so good at complex, real-world physics like gravity on the moon or buoyancy or optics, but then systematically fail at a basic geometric operation like rotation or reflection? Those seem simpler.
That's the paradox, isn't it?
Yeah.
It really highlights the nature of these emerging capabilities. It suggests that while VO3 has developed this incredibly rich, intuitive understanding of observed physics, things it's seen millions of times in its video training data.
Its grasp of more abstract, systematic, formal geometry might still be underdeveloped or even flawed.
Precisely. The failure wasn't random. It wasn't that it couldn't perform a reflection or rotation. It's that it consistently applied an erroneous transformation. Like, it would reflect the object, but always across the wrong axis, or rotate it, but always by the wrong amount or in the wrong direction.
So a systematic bias, indicating a flaw in its internal representation of those specific geometric rules.
That seems to be the case. It's a key area where its internal model clearly needs more structural alignment or maybe different training approaches.
Okay, so this naturally leads us into the bigger discussion. We've seen incredible strengths, but also these puzzling weaknesses, which brings up the classic argument about generalist models.
The jack of many trades, master of few argument.
Exactly. Right now, if you look strictly at the quantitative scores on many tasks, VO3's zero-shot performance is still often below the specialized state-of-the-art models that have been fine-tuned for years on just that one single task.
That's true. But we absolutely have to view this through the lens of historical parallel. Think back to GPT-3 when it first landed.
Right. Its zero-shot ability to, say, write code or summarize text was definitely worse than the best highly tuned, narrow models available back then.
For sure. But GPT-3 still became the foundation model, didn't it? And the specialized models started to fade. Why?
Scale and trajectory?
Exactly. Two things. First, the rate of improvement. The researchers emphasized that huge leap from VO2 to VO3 in just a few months. That suggests the capability curve is still incredibly steep.
And second,
The potential of those inference time scaling methods, like using pass at $10, if you can run the model 10 times cheaply, its effective performance jumps significantly. The argument is that the performance gap between the generalist and the specialist will likely close much faster than people think, simply because it's way easier and quicker to scale up one big generalist architecture than it is to keep pushing the boundaries on dozens of separate specialized ones.
okay, that addresses the performance gap over time. But what about the economics right now? Generating video is computationally heavy. It's almost certainly more expensive today than just running a small, efficient, specialized vision model for a single task. So why would a business switch?
That's the immediate hurdle, yes. But again, look at the LLM cost trajectory. When they first came out, inference was prohibitively expensive for many use cases.
But the costs came down dramatically.
Dramatically and predictably. We saw historical data showing LLM inference costs for equivalent performance dropping by factors of anywhere from 9x to, in some cases, nearly 900x per year.
900 times cheaper in a year.
For certain models and tasks, yes. Now, even if vision models follow only a fraction of that cost reduction curve, the economic calculation flips completely, and probably quite soon.
So the moment the cost of running VO3 or its successor becomes competitive with, say, running 5 or 6 different specialized CNNs for different tasks,
then the overhead costs of developing, maintaining, integrating, and updating all those separate specialized models suddenly look enormous. The generalist model just wins on pure economics, even if its performance isn't quite state-of-the-art on every single niche task.
economics alone could drive the shift.
I think it's almost inevitable. Which brings us to something really practical for you, the listener, especially if you're working with these models. The art of prompt engineering, but for vision.
It's just as crucial as it is for LLMs.
Absolutely. The research included a fascinating sensitivity analysis. They found that using a poorly phrased prompt could lead to success rates that were 40 to 64 percentage points lower than using an optimal prompt, even on relatively simple tasks like completing a symmetrical pattern.
Wow, a 64% drop just from bad prompting. Okay, so what are the best practices? How do you talk to a visual model like VO3 effectively?
Well, rule one seems to be remove ambiguity. Don't just say make it symmetrical. The model might not know which axis you mean. Be explicit. Make the pattern symmetrical across the central vertical axis. Give it that clear anchor point.
Okay, be specific. What else?
Second, you often need to actively fight against the model's inherent bias towards creating interesting dynamic video. If your task requires a static result, you need to explicitly tell it what shouldn't change.
Like adding constraints.
Yeah. Phrases like use a static camera, no zoom, objects remain in their final position. These are apparently essential to counteract VO's strong tendency to keep things moving unnecessarily.
And you mentioned something earlier, the motion outlet. That sounded intriguing.
Oh, yeah, that was a clever trick they discovered. Let's say the task is to solve a puzzle. The ideal final output is just the static, solved puzzle. But VO3 wants to keep animating something.
So you give it something else to animate.
Exactly. You provide a harmless motion outlet you might add to the prompt. The robot solves the maze, and then a small, colorful spinning wheel appears in the top right corner and spins continuously.
Ah, so the spinning wheel appearing signals that the main task, solving the maze, is done, and it diverts the model's residual animation energy to this unimportant element, leaving the actual solution intact.
Precisely. It stops the model from messing up the solved puzzle by adding extra unwanted animation to it.
Clever. Any other prompting tips?
One more general piece of advice was to try and translate abstract tasks into more realistic settings whenever possible. If you're testing physics, don't just use abstract shapes. Maybe set the scene in a kitchen or on a playground.
Why does that help?
It likely helps the model leverage its vast training data, which consists mostly of photorealistic videos of the real world. Anchoring the task in a familiar context might allow it to tap into those learned priors more effectively than just giving it abstract geometric problems in a void.
Makes sense. Okay, let's pivot to the limitations then. We know it's not perfect. For all its emergent brilliance, where does VO3 still consistently stumble, according to the research?
They documented several areas. Physical violations, particularly where high precision is needed, are common.
Like what kind of violations?
Well, they mentioned things like a golf ball trying to pass through the narrow neck of a vase. The model sometimes just let the ball deform or pass through, violating its rigidity.
So it doesn't always respect hard physical constraints.
Not perfectly. Another striking example was glass failing to break when dropped from a height, and they observed impossible rope movements when it tried to generate a video of tying a complex knot. The rope seemed to pass through itself in physically implausible ways.
And the robot folding a t-shirt.
Also flagged as implausible. That requires simulating really complex, precise, non-linear deformation of cloth, which seems beyond its current capability.
What about more abstract reasoning failures beyond the geometry issues we discussed?
It struggled with tasks requiring truly advanced abstract inference from 2D images. Things like accurately estimating monocular depth, judging distances from a single viewpoint, or estimating surface normals, the 3D orientation of surfaces. These are classic, hard computer vision problems, and it seems VO3 hasn't fully cracked them yet. Zero shot.
And even basic symbolic recognition could fail sometimes.
Yeah, they mentioned word search puzzles. Instead of identifying and highlighting the whole word embedded in the grid, it would sometimes just highlight individual letters seemingly at random. It struggled to grasp the sequence.
And the path planning. Beyond simple mazes.
The failures there were quite revealing. They used the analogy of the piano movers problem.
Trying to maneuver a large, rigid sofa through a narrow doorway.
Exactly. It's a classic problem in robotics and planning that requires finding a sequence of rotations and translations within tight physical constraints. VO3 apparently failed at this.
How did it fail?
Instead of finding a valid path that respected the sofa's rigid shape, it would often just cheat. It would generate video where the sofa unrealistically stretches or compresses itself to squeeze through the doorway, violating its rigid body integrity.
So again, great intuitive physics, but struggles with precise, hard constraints.
That seems to be the pattern. And finally, just general control issues were noted. While its internal reasoning might be advancing, its ability to precisely follow external control commands is still limited.
Like telling it exactly how something should move.
Yeah. Instructing cars to follow a very specific trajectory or requiring a character to move with a precisely defined force applied, it often couldn't execute these fine-grained controls consistently, even if it understood the basic intent. Hashtag outro. So to kind of wrap up our deep dive here, I think VO3 provides really compelling evidence, maybe the strongest evidence we've seen so far, that these general-purpose vision foundation models, they're not just a theoretical idea anymore. They seem to be an emerging reality.
Yeah, models that are capable of genuine zero-shot learning right across the entire vision stack, from that basic perception, through modeling the world, manipulating it, and even performing these early forms of complex visual reasoning.
And that chain of frames mechanism seems key, providing that visual, temporal equivalent to the chain of thought reasoning that was such a breakthrough for LLMs.
It really does feel like we're witnessing that shift, away from the fragmented world of specialized vision tools, towards a future dominated by a single, powerful, generalist visual mind, driven, as we discussed, by scaling laws and eventually by pure economics.
So we have this nascent generalist visual intelligence. It can perceive, it can model physics, it can manipulate scenes, it can reason across time and space.
Yeah.
We've already seen how powerful it's been to pair large language models with external tools and control systems.
Right.
So the final, maybe provocative thought to leave you with is this. What happens next? What new kinds of real-world problems suddenly become solvable when a model with VO3's capabilities gets paired not just with text prompts, but with the ability to actually control physical systems? Imagine it connected to a sophisticated robot, using its advanced inherent visual understanding and reasoning as the core engine for planning and executing complex tasks in the real world.
That definitely opens up a whole new set of possibilities. It feels like the era of generalist visual intelligence is really just beginning.
Exciting times ahead.
Absolutely. Well, that's it for this deep dive. Thanks for joining us, and we'll see you next time.